Hey, how y'all doing? Can I rephrase that? Can any of you hear me? We got a Jack says, yeah. Okay, so time to start up, I guess. Uh let's just sort of think about where we're at. We've sort of touched on chapters 8 and 9 in the lab last week. I want to mention something about 8 and 9 this week to start, and then dive into a topic which literally could have gone a week ago, or it could be a week into the future, but I think now is a good time for it. I'll call it the partial F test, and then later this week we'll talk about dealing with quantitative factors, like in the context of an experiment. I guess if I have, fertilizer levels of 0, 1, 3, 5, 15, and 30, if those were my fertilizer levels, you could presumably fit a trend line of sorts, whether linear or quadratic. There's a lot of different choices. Or I could just say those are separate levels of that factor. I could treat it like effects, but that's for later this week. And so, based on how y'all are just finishing up a test, let's start slowly, not going there. That's a little bit more challenging. Today's topic, mostly in the lab, is going to be dealing with what I'll call the partial F test. Now, before sort of picking up, just a question for y'all. Did you all finish the test? Because, that'd be really awkward if someone hadn't. Now, I got an email from one student, and it could be from this class, it could be from the other, and I just saw it, and then I sort of dashed over here to sort of sign into class, which sounds strange, but not this year. Sign into class. Yeah. Okay, so the email said, hey, can I upload my stuff, the scratch work that I did by hand? So I just want to ask y'all, did I provide a link for you to upload sort of scratch work that you may or may not have done for the test? Okay, I wanted to do that. Did any of you do scratch work, like on paper, that you'd like to submit for the sake of partial credit, maybe? Usually has very little to do with one's score in a Stat 513 class, but every so often, if a student were to upload partial, sort of scratch work, I could say, oh, now I know what they were intending to do, but there was this numeric error, and, I might want to give a different score than just a 0 for wrong. So right after class today, what I'm going to do is go turn on a thing for you to upload partial credit scratch work, and if you'd like to do that, go ahead and take a picture and upload those files, and it probably will have very little impact on most of your scores, but every so often I can really tell something that is going on right, even if the answer was not perfect. Okay, so that's my set of administrative sort of things that I can think of for now, but how warm is it in SLO? Is it really pretty warm? So I'm in Los Osos, and here it feels comfortably 75, but still I've been sweating today, and normally I sort of shiver in my house. But that being the case, maybe I'm just forgetting stuff because of the change in temperatures. Questions from you on anything administrative, please, first, before we dive in.
I was just going to ask, did you want the I did not cheat, I'm not a cheater contract uploaded, or did that first question on the exam suffice it?
I think the first question on the exam is sufficient. And usually I'll stick something like that there just as a reminder. And I think if you want to know the reason why I phrase it this way, I am not a cheater. The reason that I like to phrase it that way is studies on individuals who are asked to affirm that they are not cheaters. Literally, they cheat less than any other way of affirming that, oh, I have not cheated. Literally, if you ask them after a test, did you cheat on the test? The cheaters lie. If you ask them in advance, are you a cheater, the rate of lying about cheating drops. So I don't know if it always works, so the cheaters amongst you are filing that away for future reference. No, what it is the identification as, are you intrinsically a person who happens to be a cheater? And people don't like to admit that, even if they do cheat. And right before the test is the best way to do that. So you check the box, you're good, Jack. Anyone else? Okay, so what I would like to do to start is I'll just go ahead and share a screen. I seem to do that a lot these days. Something I never said a year and a half ago. I'm going to share a screen with you. Or very rarely would I have said that a year and a half ago. Now it's like all the time. Hopefully I'll be able to stop saying that soon. And I don't know how many of you are graduating this year or not, but next year it's likely that we'll have some more classes live on campus, but the chancellor's office is backing off their, yeah, for sure we're doing it, hopeful statement. And it really depends on public health folks at the county level. And so I'm going to be hopeful. But even then, there are some students and some faculty who, even if they were to get a vaccine, they could say, yeah, it's not good for me just yet. Okay, so we want to be respectful for those of you who are in that situation, and certainly faculty members who might die. I don't want that to happen, so I like my colleagues. Okay, so I'm not going to push anyone into it. So chapters 8 and 9. We've been touching on these things all term long. Really, we have been. Shapiro-Wilks, check for normality. You know how to do that, right? And I'll say residuals for Shapiro-Wilk is probably the best way to go. My reason for saying I prefer residuals is if you have a small number of data points, right? It's hard to look a small number of data points per group, I should say. It's hard to look in each group and spot a real lack of normality. If you have in every single group, say 5 data points that follow a perfect bell curve and then one that's out to the positively skewed direction, you would not spot that. But across 10 groups, all of which have 5 data points, if you looked at the residuals, you're going to spot the skewness pretty quickly. Okay? So residuals are the best way to assess a lack of normality. And normality is the thing that really underlies all of the hypothesis testing inside our general linear model framework. Okay? To check for equality of spread for categorical variables, once I save the residuals, I could choose to use a fit y by x, and then look for that equality of spread test, equality of variances, okay? Anytime you have a categorical explanatory variable, 1, save the residuals and use that categorical variable in a fit y by x situation to look for a lack of equality of spread. With quantitative x's, it becomes a little bit more challenging. But if you plot the residuals against predicted values, for each of the x values, you could look for funnel shapedness. If the data are, and I'm going to see if I could draw this, if the data are such that the residual plotted against, say, one of the x's, if it's funnel shaped, if you see the widening of the standard deviation of the residuals as x increases, as an example, you would say, uh-oh, problem. Okay. One way to formally check for that, indeed, just this is the graphic way of checking for it, but one way to make that more algorithmic is perhaps if you consider not the residual, but rather the absolute value of the residual. Okay? If we had the absolute value of the residual, all these negative residuals would be reflected upstairs, yeah? Okay, so I'm going to go ahead and erase just that a little bit and suggest that all the residuals should be in that cone. It's still funnel shaped, but now it's funnel shaped and positive. And if I were to fit a trend line now for the absolute value of the residual plotted against x, if that trend line has a positive slope or a negative slope, or even curvature that's statistically noticeable, if I fit a x squared term, and if the x squared or just x by itself was statistically significantly able to help me predict my residuals or the absolute value of the residuals, I would say for sure we have a problem with the equality of spread. So it's using that earlier regression technique. Let's plot the absolute value of the residuals against x. Any question about that idea? Okay. And I don't know why I just trusted Daniel. I saw Daniel saying no, and he seems to sort of like give me reactions. So as opposed to some of you who I can't even see, but so Daniel saying no and the others that I can't tell a reaction from means maybe I should pause. Any questions? Okay, then let's move forward a little bit. If you were to, like in chapters 8 and 9, in the most recent lab, and then even the lab before that with the Duncan data, if you were plotting the residuals against the x values, okay, you should see whether there's a curve or maybe even for different groups a downward trend in some of the residuals, but if in a different group you have an upwards trend in the residuals, you'd think, aha, I need an interaction. There's a lack of additivity in the model. Okay, so to summarize, the real idea is down at the bottom. If you spot a problem, fix it. At the very bottom or the last page of the lab from last Thursday, there's a select set of typical fixes for each of the sorts of problems you might bump into, categorized by, oh, I have equality of spread, but I don't have linearity and I don't have normality. Okay, what should we do in that case? What if I have normality, but I have no equality of spread and I have no linearity? So when considering these possibilities, then you'd sort of, let's try a fix. And if that fix results in something that you're happy with, well, you're good. Otherwise, you go ahead and plot the residuals against each of the x variables as well as the fitted values, the y-hats. Okay. Now, the reason why I say you should always plot the fitted values against the y-hats as opposed to just each of the x's is if there's always, for every x, a slight lack of equality of spread, or perhaps wider variability for larger x's than for smaller x's. If you have that pattern, perhaps you'll spot the problem when plotting against the fitted values, the residuals against the fitted values, instead of the residuals against each of the x's. You got to plot against both to spot all of the possible problems. Okay, any questions on that? Okay, so moving forward. Suing, oh good. And as we suggested last time, if you do have certain sorts of problems, yeah, power transformations like y to the power phi is a great way to go. There's a whole collection of things that you might want to know about that you could find in Stat 324, but I'll just say that, or 524, you get credit, graduate credit for that one. if you register for 524. There is one method that if you are looking for what is the optimal power fee, you could try what's called a Box-Cox transformation. George Box, and I've forgotten his name, Cox, came up with this method that sort of in an experimental design context, you have a way of optimizing your value fee if you're transforming your response variable y. Okay? I really just think I just try various values for y. And I like commonly chosen values of things like 1, no transformation, 2, squaring, a root, which is a power of 1/2, a 0, a natural log, negative 1/2, which is 1 over a square root. These things often, in a physical way, mean something. Okay? Or in the context of maybe a data set that I'm going to show you in a second, you could look and see, can I fix a problem, and would the problem fix of choosing a square root or a log or a power, would it actually give me terms that I'm able to utilize and make sense out of? Now, I would claim natural logs and square roots appear all the time in real life. Okay? You see stuff that is typically multiplicative. If you use a natural log, it breaks apart the multiplicative thing into something that's more additive in nature. Okay, so that's a mathy argument. But if you have data on something like the percent increase in something like the amount of debt from one year to the next for the government, you could very well see that, of course, the log transformation makes sense to use. Okay, econ and finance majors, none of whom are in the room now, quickly nod when I say that sort of thing. But yeah, stuff that's naturally multiplicative, like inflation is always every year a multiplicative process. The log, base 10, or a natural log process is a way to go. Okay, so let's look at our data on the slow home prices. And these are 1998, every single home that sold in the city of San Luis Obispo that didn't have wheels attached to it. Okay, so I'm being clear. Okay, and I guess there was one other type of home that was not incorporated into the data set. I don't know the definition of it, but let's just say a Gucci home. A home where everything is made out of the most expensive possible everything, and the price is extremely high. There were only, I think, 3 homes in that category that were eliminated from the data set, but they're all inside city limits, and every home inside city limits that sold during the year 1998 is in the data set. And if you're, let's pose to you a natural question that in the lab you'll actually be addressing. Does the price go up across the days of the year? For a comparable home, if it's sold later in the year, should it sell for more? I'm thinking inflation suggests perhaps, especially if you compare the January sold homes to the December sold homes. That's almost one full year. Okay, and so you should be able to spot inflation if it's going on. And if I remember 1998, it was about the time that I moved to San Luis Obispo, and I remember, oh crap, all the homes keep going up quickly in price. There's no way I'm going to ever be able to afford to live here. Okay, so I'm telling you the answer is yes, there was some inflation. Okay, but how much inflation was there might be the sort of nature question that you'd have. Now, the downside of this data set is, as you stretch across the different neighborhoods in town, and this is sort of your lab question, you'd expect that some sorts of neighborhoods would have newer homes, other neighborhoods would have older homes. Right around the 1996 to 2000 or so time frame is when the Tank Farm neighborhood that's sort of behind Vaughn's along Lower Broad, you know, I'm looking at a few of you and some of you are like nodding. Okay, so those homes over there were built about that time period, and that was the only neighborhood that went up during that time period. So a lot of the homes that were sold Later in the year were in that neighborhood. So homes that sold earlier in the year were not so much in that neighborhood because those homes were not really being pumped out by the contractor so quickly earlier in the year. It was later in the year that a whole bunch of them came online. Okay. But different homes, different neighborhoods. The neighborhood you're in probably impacts the price of the home, yeah? That's sort of your question for the lab. And let me set you up for one part of it, and just because we're going to tackle a different part of this data set here. Your version of the data set is a little bit more finely tuned than this, and I'm going to just go with something that matters, I think, for you for the lab. In San Francisco, if you add an extra 500 square feet to your home, will the price of the home go up? In Bakersfield, if you add 500 extra square feet to the home, will the price of the home go up? Will 500 extra square feet in San Francisco increase the value of the home much more than 500 extra square feet in Bakersfield? So the notion that we might have is the impact of perhaps the size of a home depends on the neighborhood that it's in. I told you the story with cities. You're going to be exploring that within the lab context. Okay, so I really think the size of the home square footage probably has something to do with the sales price. Before I could even assess whether there is an impact of day of year on the sales price, I need to incorporate other things into account, things that probably do matter. I really think the square footage of the home plays a role. Okay, so I'm just going to go ahead and start down that path, and I'm going to go with Graph Builder because Graph Builder is my friend. And so sales price of the home, and then size of the home in square footage. Boom. Now I see here what looks like widening as I go to the right, yes? If I were to change my response variable a little bit, I can almost see a hint of skew rightness, not much, but a hint of skew rightness in my response variable, my sales price. If I were to adjust the axis, so it's under axis settings here, I'm going to try, instead of a linear, I'm going to try a logarithmic fit. Click OK. I'm just stretching out the y-axis. Does that look closer to linear? And equal spread. Some of you are saying, others of you are saying, yeah. Okay. There is a formal way of checking to see whether it's better. Box-Cox transformation. I'm not going there for now. I'm just saying what was curved, I've now fixed. What was a lack of equality of spread, I've now fixed. I prefer, and I don't know that the lab wants you to do this, but I'm going to use the log of the sales price as my response variable and maybe fit a trend line. Let's go ahead and add that trend line in. And does it look like it's, shoot, boom. Does it look like a trend line makes sense? Linear now? Yeah. So I'm going to use the log of the sales price. And should I use log base E or log base 10? Does it matter? Probably not. But because this is money, I'm going to choose to use log base 10 because that seems a little bit more natural. So I'm going to go ahead and add a new column. And I'm going to call it log. Oh, hold on a second. Let me show you how to do this. I'm going to call that new column log of the sales price. And I'm even going to remind myself that it's log base 10 by calling it log 10 of sales price. Under column properties, I'm going to add a formula. That formula over here, oh shoot. Okay, so that formula is going to be here. I'm going to use a transformation, the transcendental version, log base 10, of the sales price. Click OK. And OK. So if I were to fit a trend line, and I'm going to now do fit model for that, does the log base 10 of sales price depend on the square footage of the home? I'd like to think so. I'll find out. I run the model. Boom. I think I'm doing pretty well. That looks like a good trend line. I'm happy with that. R squared is, well, shoot. Lack of fit, no. Residual versus predicted. R squared, 47%. Happy with that. My p-value says, heck yeah. But there's all these other variables. A whole fleet of other variables. Whether there's a dining room or not, a family room or not, a fireplace or not, whether it's, quote, landscaped well or not. Yes, the city assessor does have data on whether the home is landscaped well or not. Someone drives around neighborhoods and says, to figure out the value of your home, is it nice or not nicely landscaped? Is there a patio or not, a deck or not? Does it have a view or not? I'm wondering, do any of those things matter? Wouldn't it be nice to be able to do, rather than, 1, 2, 3, 4, 5, 7 separate hypothesis tests, wouldn't it be nice to see if by adding any of the 7, we are a better fit? That's really where we're building. This thing that we'll talk about in the lab today, a partial F test, is an attempt to say, do you have any benefit from having multiple X variables? Okay, so I'm going to define a few terms first, and then I'm going to need a little bit of calculator help from one of you to do this partial F test I'm about to consider. So first off, the logic. If I have a model where I already have an X square footage and a Y, some adjusted version of the price, I could have a richer model, a complete model with a whole bunch of extra variables in it. And if the new model is better, I'm thinking SS error should drop, yeah? Conceptually, if the new model is better, should the SS error be lower? You'd think so. So I'm going to literally just compare the difference of the two SS errors for the reduced or smaller model and for the complete model with the additional terms in it. The term complete and reduced, unfortunately, sometimes it's easy to mix the two of them up. I just think the bigger one is complete. The smaller one is reduced in size because it has fewer variables. I'm going to look at the difference of SS error between those two terms, between those two models. And then I'm going to divide through by the change in degrees of freedom between the two models. I mean, whether it's change in degrees of freedom for the model or change in degrees of freedom for error, it really doesn't matter. Shoot, I could even take the difference in SS for the model between the two things. It's just a matter of the difference of the sums of squares that change. And I'm going to divide that through by mean square error for the complete model. That is my F ratio. My F ratio. Okay, so, and I just realized I forgot to upload one file for you to use for the lab. So I will, before y'all go too much further forward, I will sort of send you that file that you'll be able to use for the lab to get a p-value from an F ratio. Okay, so let's go ahead and try the model both ways. I've got my model with just the one variable, sales price. Now I'm going to adjust my model by increasing it, if you will, make it a complete model by adding in these 1, 2, 3, 4, 5, 6, 7 additional terms. So under Analyze, Fit Model, I'm now going to recall that and then add in those additional 7 terms. And I cannot literally, I cannot, without adding all 7 in, know what the results would be. So I'm just going to add all 7 in, run that model, a whole bunch of additional output up here, but let's see if we can focus on what is just the most important for now. And let's go with back down to R squared. Oh, 51%. I earlier had 47%. Do we do a whole lot better? I'm not seeing that as a whole lot better. Okay. Can we identify which terms matter? And rather than doing individual tests like for view or whether there's landscaping or not, okay, I'm just saying we're testing all of them simultaneously. You can eliminate all of those parameter estimates, and you can eliminate even those effects tests, which get you after individual tests of individual variables. Sometimes we want to just test, hey, are any of the above helpful for me? So let's move this over here to the right a little bit. Let's move this over to the... Okay, so I need to do this and that. To get it to remain on the screen in Zoom, I cannot have a lot of it drift off of the screen. So now we've got the part we need, and for the other model, the part that we need, we also have this line around. Okay, so my 2 ANOVA tables are really what I need, and that's all. Okay, so the procedure says, let's find the difference in the sum of squares error between the 2 models, and then the change in degrees of freedom, and divide through by the mean square error. So let's go ahead and plug and chug with those values. And again, this is where I'm going to benefit from calculator help from one of you. So shoot I, and where is my blank to write on? There we go. Have you ever had one of those days? Okay, so there's my blank. I made it small and it is now on top. Speaking of one of those days, I lost my pen. Okay, so here's my pen. So I need to have, for my F ratio, the sum of squared error for one of the terms minus the sum of squared error for the other terms over the change in degrees of freedom between the 2 models over mean square error for the complete model. Now, I always write it this way at first because I know it's the difference of 2 SS errors. Which one should be first? Well, the larger SS error should be first. Otherwise, we'll end up with a negative. Okay? So the larger SS error should correspond to the model that had only one variable in it. The sum of squared error here is 1.78 for the model with all of the terms, and for the model with just one term, 1.945. So 1.945, 1201 minus 1.7839, 475. Now I'm hoping some of you are checking what I wrote down because I don't trust myself. Also, my hand is covering up the one thing that I'm looking at the screen while I'm writing this down. Okay, the change in degrees of freedom. Well, I had 8 degrees of freedom in the one model and 1 in the other. So that's 7 degrees of freedom is different. The change in degrees of freedom is 7. Now that's the change in degrees of freedom for the model. I circled the 8 and the 1. I could have also circled 312 and 319. Also, the difference of those would be 7. Okay. We're going to divide that through by the mean square error for the complete model. That's the model with all of the terms in it, all 8 terms. And that's a 0.0057818. And I said that wrong. 0.005718. Okay, so I know some of you are better than me at checking this, but did I at least get the numbers copied down correctly? This is one of those, it's important to do it because if you get it written down wrong, that could be frustrating. Jack says yes. So if I'm wrong, Jack's wrong too, and you blame both of us, please. Okay, so calculator help here. I need to know the overall value of this F ratio.
I got 4.026.
4.026. Okay, because I'm also looking for one other thing that I was going to share with you. I'm hoping someone will actually verify that as well. Did someone else?
Yeah, I
Oh,
concur with
yes.
that number.
Concur. I love that word. Okay, so I happen to have an F-test p-value calculator, and this is the one thing I neglected to put into the lab, and I'm going to be doing shortly before turning you loose. Okay, or better yet, we'll take a 2-minute break or 5-minute break or whatever. So when I put you in the groups, great, but don't worry about it. It will appear in the lab shortly, and then I'll just email everybody this p-value calculator. So I've got an F statistic. I need 4.026. Put that in. Well, the test degrees of freedom is our numerator degrees of freedom. And when I say numerator degrees of freedom, do y'all spot the 7 is, even though it's in the denominator of the numerator, it's still in the numerator? Okay, so what we call numerator degrees of freedom is the change in degrees of freedom between the two models, 7. Denominator degrees of freedom, that is the degrees of freedom in error. So that mean square error was found by taking our 1.7839, etc., divide through by 312. So I've got to have a 312 here. So 312, boom. My p-value is now 0.0003. Yay. Okay, so I've got an answer here. The question is, the null hypothesis is none of the 7 terms that I added play any role at all in predicting the response y. None of the 7. The alternative is at least one of the 7 is important, has a non-zero slope or a non-zero effect somewhere. Null hypothesis, none of the 7 matter. Alternative, at least one of them does. Okay, so we've got a p-value and a conclusion. So let's get back into what this analysis says. With p-value of 0.0003, I would say at least one of my terms is helpful. At least one of the variables is helpful. Now, in this case, I found at least one of them was helpful. I might want to now go back and more carefully say, which one was it? I might want to look at those individual slope tests. But the reason we often like to do one of these partial F tests is the following. Toss in a whole bunch of things that you think probably none of them matter. But if at least one of them does, it will pan out. It's a way of, rather than doing multiple tests, each of which has a 5% rate of type 1 error, like if you had to do 10 tests, each of which had a 5% rate of type 1 error, there's about a 50% chance that at least one of those 10 variables will appear statistically significant. This is a more parsimonious way of checking at least one of them. Hey, is one of them helping me? Or do none of them really prove themselves? So we can with fewer tests, check more terms simultaneously. Now, you might think, hey, that sounds like what you could have done when you were literally doing those tests for categorical factors, like in the hand washing example. You know, are there any effects of any of the types of soaps on or hand washing methods? Or even in the context of the Duncan data, hey, is there a difference across the 3 career types? Literally, the method the software utilized to answer that question was they did a partial F test. They tried it once without and once within with those 3 different career types. The analysis you would get, okay, if you were to do the partial F test by hand is the exact same thing as if you had the categorical factor and just asked JMP to do the effect test. So by default, you do get the effects test, but this is here gonna tackle again a challenging question that we have not yet addressed. What if you had to do multiple hypotheses, multiple betas, if you will, all 0 simultaneously? Null hypothesis, all 0, alternative, at least one is non-zero. I would want to close out by saying the real benefit of this is like you'll see in the lab today. I might want to ask the question, is there any impact at all anywhere of the neighborhood you're in on the price of the home? If you have either the categorical variable for neighborhood or an interaction between the categorical variable for neighborhood and then say square footage, if either the intercept or the slope is adjusted, neighborhood matters. If either the intercept or slope is adjusted, neighborhood matters. And JMP has thus not, so far, not been able to answer that question. Would the intercept or the slope be adjusted? You could do a partial F test. Fit the model with both terms, the neighborhood, and then also the interaction between neighborhood and square footage. Or you could fit the model without either of them and compare the two. Okay. So I think that's about it for now. Other than there is one more example of a partial F test that I'll want to start with next time. Literally, a partial F test could also be utilized cleverly to see if 2 of your subgroups are literally identical. Remember when we had the 3 different types of careers? There's the blue collar, white collar, and professional. It seemed as though professional was higher and the blue and white were down below, lower. Is it just 2 types of careers, professional and non-professional? Or is it 3 completely different types of careers? We'll start with that one next time. So I need to add this to the lab, the partial F test calculator. And do you want to just take a break right now, or do you want me to put you in the groups and then it'll take me a minute? Do any of you? Okay, I'm thinking this through in my head and none of you are commenting. So I'm just going to go ahead and upload it now. And if you get up and wander away, because, you know, you feel like drinking a beverage and there's a soda machine down the hall or you've got a refrigerator, that's fine. It'll take me about 2 minutes to get this uploaded into the lab for y'all. And then I'll put you in the groups. So I apologize for forgetting to do that earlier. Oh, well, that's not it either. You ever have so many windows you forget what you're doing? That's my life. Okay, so in the lab.
And your shirt.
Oh, yeah. Have you seen this one before?
Stay on the bottom.
Yeah. I've actually... Go ahead.
What does it say on the bottom?
Oh, yeah. So I can't even read it because it's backwards for me. If y'all read it, I'll pull it up as you go.
My mind is like an internet browser. I have 19 tabs open. 3 are frozen. No, I can't see.
Yeah.
I-
Okay, is that?
Where the music is coming from.
Yep.
Those tabs open at the Merrymaker?
I'm sorry, what?
Is one of those tabs open at the Merrymaker?
Hey, good question. Yeah, no. I think they're remodeling right now, in case you're wondering. I don't know if it's open again. But yes, it's one of those classic dive bars. I would recommend going if you drink because it's an experience, or at least it used to be. Maybe I don't know if it isn't anymore. I'm sorry. Okay, I found the file and I'm now going to add the additional thing. And it's okay, boom, got it. Open. Okay, so I've just saved. It appears to me if you reopen or refresh the Lab 8, you should see this one thing called the partial F test p-value calculator, which will get you the p-value if that's a problem. I'll be emailing y'all shortly, but I'll put you in breakout rooms now. And just for fun, I'm going to open all the rooms and we'll see what happens. I'll have to shuffle some. Oh, hold on. No. Jack, where do you go to? I forget.
4, I believe.
Oh, you're in 4. Ted, where do you belong? Aren't you in 7, Ted?
Yeah, 7.
Okay, so 7. I always forget who goes where. Isabella, where do you go? I forget. And I know you're always in the wrong room.
4.
Perfect. Okay. I'm just going to go ahead and open this and see what happens. And then raise your hand if you're in the wrong place and you want me to move you. I will be happily able to do that. Okay, and then this always happens. Ali, you're 10.
You, Chen, and Josh are both in 4.
Got it. I could do that.
Harrison is 4 and 6.
Harrison and East in 6. I could do that. Boom. And Joseph,
Thank
where do
you.
you want to be?
Room 10.
10. Got it. You're in 10.
Thanks.